So what do you think we're looking at? Concentration as a function of what there? Time, right? And what gives us a relationship between the concentration and the time? The integrated rate laws, right? So you plug this into the integrated rate law. When you plug it into the integrated rate law, that allows you to solve for t1/2 in this scenario, right? So if you have a at t1/2 is equal to minus k t1/2 plus ln the initial concentration, right? So remember, you just plug this into that expression right here, do a bunch of algebra, and you can solve for the half-life there. That's how we did that, right? The integrated rate law gives us a relationship between concentration and time, and you just define the time that it takes to get half the concentration as the half-life. And so for a first order reaction, that was the integrated rate law, right? So that was a first order reaction. Does it depend on the concentration at all, the half-life? No, right? Because the concentration doesn't show up in any expression here. The initial concentration doesn't show up at all, which means that for each half-life, every time you successively half the concentration, so you just multiply it by 1/2, it takes the same amount of time for that to happen, right? And so we also looked at an expression, or you guys found the expression for, where was it? The 0th order reaction. So the 0th order integrated rate laws. Logs, first order. So first order, all the way. So that's farther than I went. For 0th order, all right, let's just go through what a 0th order reaction was. It was the concentration as a function of time is equal to minus kT plus the initial concentration, right? It gives you what kind of relationship between the concentration and time? Linear, right? This is just an equation for a line. They're linearly proportional, which means as one increases, the other decreases because we have a negative slope in this case. If we plug in at t1/2, so t equals 1/2, a0, we plug this in, we get 1/2 a0 equals minus kt plus a0, subtract that from both sides, minus 1/2 a0 equals minus kt. So then, and this is 1/2 at this point because it's at t1/2. That then gives us the concentration of a0 over 2k equals the half-life. All right, so we can always make this substitution when we're trying to determine what the form of the half-life is. Here, does it depend on the initial concentration? Does the half-life depend on the initial concentration here? Yes, right, because it shows up right here. If the initial concentration is large, then the half-life is large as well, right? That means as the reaction progresses, the concentration gets lower and lower, so the half-life gets shorter and shorter. And we visualize that a little bit by looking at the successive shortening of the half-lives when we plotted it. All right, so that was just reviewing what we ended with last time, and where here we have the two plots. I'll bring them up in a second. Give you guys a second to write. right? So this was the plot that we looked at. This is for a first order reaction. You see that this half-life, every time you half the concentration, which is at each of these dotted horizontal lines here, it takes the same amount of time to do that, right? And that's just because the shape of the curve, the slope gets smaller and smaller as the reaction goes on. Whereas for a zeroth order reaction, it's just a linear plot. The first half-life is a certain value, then we go to the second, halving the concentration one more time, and you see that because it's a linear line, it's linear, that the half-life also gets smaller as the reaction proceeds, because the concentration you're starting from at that point is smaller than it was initially. Right, this is a large initial concentration. Once you get to half of that, the half-life should be halved as well. And that's because those are linearly related. Okay, any questions on that? Alright, so that's where we ended off with last time. Any questions? Everyone feel comfortable with that? Remember, we also discussed, we went through a relatively lengthy problem looking at how if we have 10% decay, how long does it take to have 90% of the original sample left over? And that was, nuclear decay process was a first order process. And so we plugged that into our relationship for our first order reaction, did a bunch of algebra again, and then solved for the time it takes. Here, the half-life was given and not the rate, which means that you had to solve for the rate constant using the half-life equation. Right, so kind of everything we have up to this point is we'll just do 0 on first order. We have let me write a number here. First order reactions, so we have our rate law for 0th order reaction, where it's just K is equal to the rate constant, because the rate of reaction doesn't depend on the concentration at all. For a first order reaction, the rate of reaction is equal to the rate constant times the concentration of the reactant, right, to the first power. That's why it's called a first order reaction. We have our 0th order integrated rate law, which is concentration at time t is equal to minus kT, concentration at time 0. And then our first order integrated rate law, the concentration, the natural logarithm of the concentration at time t is equal to minus kT plus ln the initial concentration. Then we have our half-life relationships. The half-life is equal to initial concentration over 2 times the rate constant. And for first order, the half-life is equal to the natural logarithm of 2 over the rate constant. And those are all the equations we have so far, right? And so for each of these, you're good, you can let, oh, you're just getting hands sanitizer, you can let the door shut, it doesn't matter. And the only other thing that we talked about up to this point that introduces a new equation to this is just the temperature dependence, right? Which was the Arrhenius equation. But that's kind of separate. That's the temperature dependence, which was K is equal to A e to the minus EA over RT. Right, where, what was A here? What did A represent? It was the frequency factor, right? That was the number of attempts to approach the transition per unit time, is how we look at that. And then EA was the activation energy, the energy barrier it has to overcome for the reaction to happen. And then RT, R was what? Ideal gas constant, and then T is the temperature, right? And this is saying what fraction of the molecules have enough energy to actually overcome that barrier. And this is all equal to what right there? What is that K? Is that uppercase or lowercase k? Lowercase, right? Because this is the rate constant. The rate constant is where the temperature dependence of the rate of the reaction shows up. So in this lowercase k. All of these are all done at constant temperature. If you change the temperature, it's equal to, how it depends on the temperature is equal to the Arrhenius factor right here. Okay, so I know it's a lot of, different equations going back and forth between them, and then I'll have a chart at the end of today's slides as well to discuss, or to kind of summarize all of these results as well. Okay, and so then we ended up talking about graphing first order reactions, right? Where if we plot the data in a specific way, if it matches the order of the reaction, then it'll give you a straight line, right? And so for a first order reaction, y, right? If this is just our equation for a line, what was y equal to here? How do we have to plot this? So this is for an arbitrary reaction of SO2Cl2. Yeah, you have to plot the natural logarithm of the concentration. That's our y variable here. So ln SO2Cl2 is equal to, there's a slope here. What is the slope equal to? Negative k. There's already a negative sign here, so this is just equal to k. So this is going to be minus the slope, this value right here, is equal to k, and that's lowercase k, the rate constant, times the time, which is like your x variable in the equation for a line. And what was the intercept here? What was this? Yep, this was the natural log of the initial concentration of SO2Cl2. Right, so when you plot the data this way, if you get a line, that means that you have a first order reaction. If it deviates from a line, meaning that you have a straight line right there, but then the actual data points form a curve, then it means you don't have a first order reaction. Right, so there's a number of different ways that we can hint or come to the conclusion about the order of our reaction. One was plotting, or not plotting necessarily, but looking at the experimental rate law and determining the coefficients, which is what you guys did in lab, right? You measured the rate of the reaction and then see how that varied with the concentration. Another way is if you have the concentration versus time, you plot the data in three specific ways, one for 0th, first, and second order, and whichever one gives you a line tells you the order of that reaction as well. Right. Any questions on this? Just because I know this is kind of a foreign concept, right? So a lot of times when people are doing big data and stuff like this, they're manipulating, massaging data to give you trends that you can actually see here. And this is one of the ways that you can observe a trend without actually doing any type of calculation. So sometimes if you're a visual learner, this will make more sense than doing the experimental rate laws, because here you're matching a plot to what you expect it to look like. How do you guys feel about plotting the order reactions? Maybe, yeah, I can understand. This is when I was an undergrad, this took me quite a while to understand this concept. Because this is just the beginning. If we can go on in chemistry, it gets, even more, the data gets a lot more manipulated than this too. But you'll have practice doing this in lab as well. Okay. So here, use the graph below to determine the concentration of SO2Cl2 at 1900 seconds. So here, all you're given is the plot. I believe it's the same one from the previous one. So determine what the concentration is at 1900 seconds. Right? So what's given to you just from given this being given this plot here, and how can you use that to solve for the concentration at an arbitrary time, right? So you see that 1900 seconds is out of the scope of this plot, or out of the range. Like 5 tries to put that into the calculator. All right, so what do you need from the plot and the equation of the line on the plot here? All right, y is equal to what from the previous page? ln SO2 Cl2 at time t is equal to minus 0.000290 t minus 2.30, right? And so you can actually take this and just plug in the value for 1900 here, right? Because you already have the concentration as a function of the time. So you plug in 1900 to this, you get ln SO2 Cl2 at 1900 seconds is equal to minus 0.000290 times 1900 seconds. What are the units of the slope here? One over seconds, right? Inverse seconds. How do you know that? Well, the natural logarithm is a unitless quantity, so this whole thing is unitless. And then for anything to be added to another number that's unitless, it has to be unitless as well. Which means if we're multiplying this by seconds, that's going to have to be inverse seconds. So s to the minus 1. So those units are going to cancel out. You can also realize that this is a straight line for the plot of the natural logarithm of SO2 Cl2 versus time. That tells you it's what order reaction? Right, if it's ln SO2 Cl2 versus time, and it's a straight line, what does it tell you? First order reaction, right? In a first order reaction, we know that the units for the rate constant are inverse seconds, right? And then the slope, we know for this plot is equal to what? This is the rate constant, first order reaction, means that the units of k are equal to 1 over seconds, or s to the minus 1. And we can write that both ways. And then you subtract minus 2.30 from that. That'll give us something like ln SO2 Cl2 1900 is equal to minus 2.5851. And then how do we solve for the concentration here?
Just e to the third. That's it.
We just exponentiate both sides, right? E, and also bless you, e to both sides. What happens to e to the logarithm? Yep, those are inverse operations, so those get rid of each other. So that becomes a concentration of SO2 Cl2 at 1900 seconds is equal to 0.0578 molar. All right, did everyone get that? All right, so there's a couple checks along the way. You know that this has to be unitless because it's first order reaction, that's a line like that. So you can interpret that just by looking at the plot here. And then you also know that this just gives you a relationship between the natural logarithm and the natural logarithm of the concentration and the time. So you can actually just plug in the time there, and that'll give you your answer. Right, and I know you don't necessarily need to do this for the problem, but we're just constantly going back and forth to remind ourselves of, what are the units, what order reaction are we looking at? Because if we know the order of the reaction, and you have your index card with your different integrated rate laws, experimental rate laws, half-lives, and Arrhenius equation on there, then you can know which equation to go back and forth between. All right. Any questions on that? What's in it?
So in order to get the concentration, because I had gotten up to the point where it was negative 2.851.
This part right here?
Yeah.
Mm-hmm.
So I thought that was the answer. So in order to get the actual concentration, you have to cancel out the log.
Yeah, the logarithm right here, right? Because this isn't just the concentration at time t, it's the natural logarithm of the concentration at time t. And that's just a consequence of the fact that this is the first order reaction. And the way we know it's a first order reaction is because the plot of the natural logarithm versus time t gives us a straight line. And so whenever we're getting rid of, whenever we want to solve for anything that's a logarithm, in a logarithm or an exponential, we can exponentiate both sides, meaning raise both sides up into the exponent for e, in e to the natural logarithm, or 10 to the log base 10, those are inverse, so they cancel out with each other, so then this gets pulled down like that. And then you just put this in your calculator. Mm-hmm. If it was a zeroth order reaction, then you would be right. This would just be the concentration right here, because it would be it wouldn't be the natural logarithm, it'd just be the concentration there. Mm-hmm. Yeah, good question. And so I know I said, oh, well, the natural logarithm is something that's unitless. That gets a little bit more metaphysical. We talk about, well, if this is unitless, how come you take the exponent of it, it all of a sudden has units? But that's a little bit more mathy beyond the scope of this class. Okay, any other questions on that? So again, it's just a realization that algebra is relatively minimal for a problem like this. All right, so here we have another one. Shown below is a graph of the concentration versus time for a decomposition reaction. Determine the order of the reaction and the value of the rate constant here at this temperature, right? So all the integrated rate laws are all done at a very specific temperature. So this one is almost like an observe the plot and determine these things just by looking at it, right? So here you don't have to do any type of calculations. So just give you guys a second just to kind of look at it. All right, so what's the order of this reaction? First order, and how do you guys know it's first order? Yep, because we have the natural logarithm of the concentration as a function of time, and it gives us a straight line, right? So this implies that it's a first order reaction. And what about the value of the rate constant? What is the value of the rate constant here? It's the value of the slope, right? This is always whatever is given in front of the x variable here, which is, just written as x here. So this is probably plotted in Excel, and then, put the equation on the chart. So that's going to be equal to the rate constant. So K is equal to 0.0461. And then what are the units of this according to this plot? So it's inverse seconds usually when we talk about this, but what is the x-axis here? It's in hours, right? And because this is just spitting out a slope for this very specific plot, that means that this right now is given in units of inverse hours, right? And that's just because you're plotting hours here. You can always convert this to seconds. If you wanted to convert this to seconds, how would you do that?
60 times 60.
Maybe 0.461 per 1 hour. Just do a unit conversion. 1 hour is equal to 60 minutes, and then 1 minute is equal to 60 seconds. Hours cancels out with hours, minutes cancels out with minutes, and all you're left with is inverse seconds when you do that. Alright, so the 60 times 60, the denominator is going to give you the conversion to seconds. You don't have to do that for this problem, but because this is just asking for whatever the value is. Data.
Can I ask why you don't include the negative?
You don't include the negative because the slope is negative here. And then you know that the rate constant is going to be a positive quantity. So rate constant is always going to be a positive quantity, and they actually already include the negative sign in the slope.
If they didn't have the negative sign in the slope, would you include the negative?
You would include the negative if you did do that. And so I guess in a way I did include the negative because technically the actual equation for a first order reaction is ln A at time t is equal to minus kt plus ln initial concentration. So this whole slope right here, this minus 0.0461 is equal to minus k, because that's just what's in front there. So when you do that, those two negative signs are going to cancel out. All right, so we're saying minus k is equal to minus 0.0461. Negative sign on each side just cancels out. Good question. All right. Okay, so we'll have more practice with that over time. So I'll let you give you guys a second, and then we're going to start talking about second order reactions, which is basically everything that we've talked about with zeroth and first order, except now you're going to be looking at plotting it in a one last way, right? So you're going to be looking at how it's plotted. Is it giving you a straight line? Except it's not going to be ln, it's going to give you another type of plot. All right, so for second order reactions, we have the general form that the rate of the reaction is equal to the rate constant times A to the power of 2, right? And this was equal to minus the change in the concentration of A over time. We do some calculus, and we get that 1 over the concentration at time t is equal to this rate constant times the time plus 1 over the initial concentration. Right, so you kind of get set up the same type of separable differential equation. The only difference here is that the negative sign is going to end up canceling out. And then you get this form for our second order integrated rate law. Order integrated rate law. Does anyone remember what the concentration, or sorry, what the units for the rate constant are for a second order reaction? All right, so we can look at it right here, we can determine it, and we can also look at this equation, and both will tell us what the units are.
Was it polarity squared over second squared? Or something like that?
Not quite molarity squared over second squared. Think about if this has units of time multiplied by something, right? And what are the units of this whole thing right here?
Oh, inverse molarity, inverse second.
Inverse molarity, inverse second. And so we can rationalize that two ways, right? Here, what are the units of the reaction rate always?
Molarity over seconds.
Molarity over seconds, right? The same way of velocity, speed. The reaction rate always has to be positive, molarity over seconds. Alright, so this is molarity over seconds. we already have molarity squared here, right? We need to match molarity over seconds, which means we have to cancel out 1 unit of molarity. So we put 1 in the denominator, and it's per second, so we have to have per second there, right? And so we can set up an algebraic equation to solve for the units, and we'll do that. We'll do that more and with other units as well. The other thing you can look at is you can look at this second order integrated rate law, and you know that for two things to be added together, what has to be the same for both of them?
The units.
The units have to be the same, right? And we know that this is multiplied by time. So if this is, what is the unit of this whole thing right here? 1 over molarity, right? So that means that this has to be units of 1 over the molarity, right? Which means that we just need 1 unit of time to cancel out. So this has to be units of 1 over the molarity times 1 over the time. So the units of time cancel out, all you're left with is units of 1 over the molarity. Right, so again, units always tell us if we're on the right track, and units should always be working out. Right, so that's our second order integrated rate law, which gives us a relationship between the concentration at time t as a function of the time, right? And so if we were to plot this, we would then plot it another specific way we'll talk about in a second. But before we talk about how we plot this to determine the order of the reaction, we can also define a half-life for the second order integrated rate law. And so why don't you guys take a minute or two and see if you can come up with what does the half-life for a second order reaction equal to, right? And and ask yourself, does it depend on the initial concentration or not? How does it depend on it? And think about what you have to do to actually solve for the half-life here. What's the substitution that you make here? Like, where should you start from?
T1 half.
What T1 half?
Oh, you sub.
Mhm.
It's not the concentration for a time, right?
Yep, a T1 half is equal to what? After 1 half-life, what is the concentration equal to in terms of the initial concentration?
1 half.
1/2 the initial concentration, right? So that means you get, at T1 half, you get 1/2 the initial concentration. So you take this value, or that expression, and you just plug it in to that A at T here. And then you just replace T1 half with, or T with T1 half, right? And then you solve for T subscript 1/2. Once you make this substitution, then you pretty much are just doing algebra to solve for T1 half there. Right, so when you're starting from here, think about collecting like terms, and collecting the initial concentrations together, and then rearranging everything else. Okay, so how do we rearrange this? How can we rewrite, let me get the laser pointer, this expression right here? How can we rewrite that? That's this thing. Go ahead.
As 2 over
Mm-hmm.
2 over the initial concentration?
Yep, it's the same thing as writing 2 over the initial concentration. How do we know that? Well, this is like 1 over the initial concentration over 2. 1 over a fraction is just the inverse of that fraction. So this goes to 2 over the initial concentration. So if that's 2 over the initial concentration, I'll move it here. We get 2 over the initial concentration is equal to KT plus 1 over the initial concentration. What's the next step here?
Subtract the 1 over initial
Yep.
concentration.
Subtract 1 over the initial concentration from both sides. So we get minus 1 over A minus 1 over the initial concentration. Right, what happens to the initial concentrations here? They go to 0 plus minus, that goes to 0. So then we get 2 over the initial concentration minus 1 over the initial concentration equals KT. How does this simplify? This just goes to 1 over the initial concentration, right? So this is just a fraction. It's like if you had 2 over 3 minus 1 over 3, right? If we just treat that as a number, 2 over 3 minus 1 over 3 is 1/3, right? So it's even though there's a variable down here, whatever the initial concentration is, you're treating it as if you're just subtracting 2 fractions where the denominator is just any number. Right, so that simplifies to 1 over the initial concentration is equal to KT. T1/2, sorry. I didn't write the 1/2s for all of these. 1/2. Right, is everyone comfortable with that? How that simplifies like that? Right, like I said, it's the same thing as you have 2 over 3 minus 1 over 3. That's just 2 minus 1 over 3. 2 over A naught minus 1 over A naught is like 2 minus 1 all over 1 A naught. And then what do you do for the last step here? Yep, divide by K to isolate T sub 1/2. Right, so we divide by K. 1 over K. On the right-hand side, what happens to the rate constant? Cancels out. So then that gives us our final expression, which I know is kind of sandwiched here. T1/2 equals 1 over K A naught. Right, so that's our expression for the half-life for a second order reaction. And I know this can be a very foreign concept, kind of deriving your own expression. But I think the important aspect here is, understanding what the definition of the half-life is and how do we use that to come up with an expression for the half-life. The algebra, can be annoying, but it's just a small part of getting to your final answer. This is the more important realization for doing something like that. All right, and so does this depend on the initial concentration? And how would you say those two are related, the half-life and the initial concentration? They're inversely related, right? Which means that if the initial concentration goes up, what happens to the half-life? It gets smaller, right? Because if this goes up, it's like 1 divided by something large, that's going to go down. If this gets smaller, 1 divided by something small, the half-life is going to go up. So they're inversely related to each other, which means as the reaction is going on, the half-life is getting longer or larger and larger. Right, so as the 0th order, the half-life gets smaller and smaller as the reaction goes on. For 1st order, the half-life stays the same as the reaction goes on. And then for 0th or 2nd order, the half-life gets longer and longer as the reaction goes on. So thankfully, nuclear processes are not 2nd order reactions. Otherwise, it would never fully decay, right? Okay, any questions on that? All right. So we'll go over some examples of some second order reactions. Those are largely the same. Solving for the concentration at time t is really the same for any of the order reactions. The only difference is what equation are you going to be starting from. So that's the important part. What equation do I need to start from? And when I'm giving you a quiz or an exam or something like that, that's where like the large majority of the realization or the points lie is, okay, where do I start from and what's the relevant information that I'm being given? All right, so let's take like a 10-minute break right now. We'll come back, we'll finish up talking about second order reactions, and we'll talk a little bit about collision theory and maybe be able to get into a little bit of reaction mechanisms today. All right, so let's go ahead and continue. All right, so we derived our expression for the half-life. We see that it depends inversely on the initial concentration. So here we have a particular second order reaction. You're given the rate constant, the units as well. So how long does it take for the concentration to decrease from 0.0030 to 0.0015 molar? So I'll give you guys a minute to think about that, and then we'll go ahead and work through it. My bad. 2025. All right, so how do you guys want to solve this?
Integrated rate law.
So we can use the integrated rate law. Rate law. Does anyone know another way we could solve this? Maybe a little less algebra. If you look at the two concentrations, the initial and the final, what do you notice about them? One is half the other, which means if we're looking for the time, what's the other thing that we can solve for?
Oh, for the half-life.
The half-life, right? So the other way we can solve for it is using the half-life, the expression that we just derived. So the half-life, which is the time it takes for the concentration to half its initial concentration, is equal to 1 over 2 times, not 2, 1 over k times the initial concentration. Integrated rate law at time t equals k t plus 1 over the initial concentration. All right, so we can use integrated rate law if we want. It's going to take a little bit longer, or we can just use the half-life, because the half-life tells us the time it takes to reach half the concentration, and by looking at the concentration values, we can see that it's halves, right? So if we plug these in, we can do 1 over a t minus a naught divided by k is equal to the time, or here we can just plug it in, t1/2 equals 1 over 0.775 molarity inverse seconds times 1 over 0. And which concentration do I put in here? 0.003, because that's the initial concentration, right? 0.003 molar. Let's make sure our units work out. Molarity and molarity inverse, what happens to that? Cancels out, right? And so we have 1 over inverse seconds in the denominator, which gives us units of, right, if we have inverse seconds in the denominator, that gives us seconds in the numerator, right? So we have units of seconds. Makes sense because we're looking for a time here. So if I plug all of that in, we get 1 divided by 0.775 times 0.003. I get 430 seconds. Let's see if I plug everything into the second equation. So it would be 1 over 0.0015 minus 1 over 0.003 molarity times the 1 over the rate constant 0.00775 inverse molarity inverse seconds. So that's what I'm plugging in for the expression down here. We see we have 1 over molarity here, and then we have 1 over inverse molarity here. Molarities cancel out, inverse seconds in the denominator, so we'll get units of seconds again. So we should get the same answer. 1 divided by a smaller number minus, so this whole thing is going to be larger than that number, so it isn't negative, so that's also a double check here, right? This fraction is going to be larger than that one, so this whole quantity is going to be positive. That's another thing that we could see here. If we're on the right track, if we get a negative time, then that doesn't really make sense, so. At least not in classical mechanics. Okay, so if I plug all of that in, it's a bit more laborious and laboring. 1.5 minus, I added too many zeros there, damn it. So this is why it's good to practice with whatever calculator you're going to use on the exam, so then you know how to do everything before it's stressful. 0.03 enter. So that's 2, which makes sense. It's a half the concentration. So it's going to be 2 divided by I messed up. 1 divided by 0.0015 minus 1 divided by 0.003 divided by 0.775. And I get the same answer both ways for 430 seconds. Okay, so it works both ways. You can do it either way, you get full credit. This is just going to be a lot simpler, and also, you know, it's more of a realization you come to here. 430 seconds. These are the same. Lee?
Sir, I still don't understand why there's no negative sign in front of the constant for the numerator and third law.
Why there's no negative sign in front of the constant? It has to do with the calculus. So if you go back here, the way, remember, we integrate, well, it's a separable, so this is an aside, so if you don't want to learn about it, you can tune me out right now, but it's minus dA over a squared equals kt, so we can just bring the negative over to this side, sorry, k dt. When we integrate both sides of this equation, this is 1 over this variable squared. The integral of that, you pull down this number, which is 2, and it's in the denominator, so it's a negative 2. So you pull out a negative 2, and that negative is going to cancel over here. So what this ends up going to is it goes to minus 2, 1 over a at time t minus 1 over a naught. If we're integrating it from 0, or not 0, we're integrating it from the initial concentration to an arbitrary concentration at time t equals minus kt. So those two negative signs are going to cancel out, and then when we rearrange this 2, that 2 is going to, I'm sorry, I don't bring down a negative 2, I bring down a negative 1. And if you go into calculus, you'll learn about why an integration works that way. Is anyone in calculus right now? Nay. But that's why there's no negative sign for this integrated rate law. I could have just said the calculus, but what was the point of going through all that school if I don't get to do it every now and then, right? Okay, so these both give you the same answer either way. Also, another reason is if you think about this, right? This is 1 over a value, which means as time goes on, or as this gets larger and larger, you know, that value gets smaller and smaller. So for it to be a decay, this has to be a positive value right there. Right, in the first order rate law, that's like an exponential decay. So we have e to the minus kt. And in a 0th order, it's a line with a negative slope. Here, because of the specific way it is, 1 over the variable, that's already a decay process. So you want that k to be that slope value to be positive there. All right, any questions on the question itself? Okay. All right, so then how long does it take for the concentration to halve again? Do you expect it to take longer or shorter? Right. Let you guys think about that. So if it's halving again, what are you going to use? K in the initial concentration, that's related to what quantity? Half-life, right? So we're going to use T1/2 equals 1 over K, the initial concentration. And it says having again.
It's going to be larger this time?
It's going to be larger this time. So why is it going to be larger?
Because the relation
Between, yeah, you know they're inversely proportional, right? So you know that if this goes on, and the initial concentration now is half of what we originally started with, right? So the initial concentration has gotten smaller. And we can confirm that just by plugging it in. T1/2 equals 1 over 0.774 inverse molarity, inverse seconds, times 0. And what do we put for the initial concentration this time?
0.0015.
Yep, 0.0015, because that was our final concentration for the first part of the question. For it to half again, that means that we're starting from this concentration. All right, our final concentration becomes our initial concentration for this second part, molarity. And so when we plug that in, we get 1 divided by 0.774 times 0.0015. And that gives us T1/2 equals 861 seconds. And that's exactly what happens. Arhelia?
Why is it 1774?
Did I write it wrong? 775, yeah, my bad. Thank you. I didn't write it wrong again, did I? No, okay. Did I write it wrong over here? 5, okay, I think I did it right on the first page. All right, and again, this is related to when we did the plots of the concentration versus time, looking at how long it takes for each concentration to halve. Remember, for the 0th order reaction, it would get shorter and shorter as we go down the line, right? That vertical dotted horizontal line gets smaller. For a first order reaction, it stays the same for each interval. And now for a second order reaction, it's going to get larger and larger for each interval. Okay, any questions on that? All right, so I'm going to go back to this one with all the plots on it, and we can now draw a second order reaction. And if we do that, we can show, and I'll do my best to illustrate it by drawing it, right? So we start with some initial concentration, and then it's going to initially decrease fast and then change even faster than the first order decay, right? This is exponential decay. here, the slope is gonna be increasing or decreasing at an even larger rate. And so hopefully I drew it well so that we can see this, that if this is our initial concentration, so this is our concentration of A as a function of time, say it's 1.0 molar, then this is gonna be 0.5 here. If I can guesstimate it, 0.5. I used blue there. So this right here is the first half-life. Then this is when we halve the concentration one more time. So the concentration just gets halved one more time. But now because it's decreasing at a much larger rate, for it to intersect this curve, let's do that right here, that's gonna be the second half-life. It's terrible. T 1/2 2, that's T 1/2 1, right? So the initial time it takes is this half-life right here. We have a steep decrease in the concentration initially, and then it takes a long time to halve the concentration one more time. And that just has to do with the shape of all of these different curves right here, right? Because this starts decreasing even faster, it means it's gonna take a lot longer to actually reach half the initial value again. So this is the second half-life if we started at a concentration of 0.5. So here, the second one gets longer. Here, each half-life takes the same amount of time. And then here, each half-life gets excessively smaller. So those are visual representations of the plots or the relationships we came up with for the first order, second, and 0th order half-lives. Is anyone confused in that? I know it's a little crooked right here, that's because I think I drew it a little too flat right there, but you guys get the idea. It's going to take a lot longer to reach that point because the change in concentration is getting slower and slower. Okay. So then next, we'll talk about plotting the second order rate law. So similar to the other ones, if we plot the data in a certain way, we can make it so that if it fits that order of the reaction, we should get a line. So what's going to be our y variable here, you guys think? Yeah, the inverse concentration at time t, right? So this is y. Our slope should be k. Oops, sorry, that's going to be m here. Our x variable is the time, and then our y-intercept is going to be what? One over the initial concentration, right? So this is going to be b. So we can write this another way. Y is equal to 1 over a at time t. The slope is equal to k, and then the y-intercept is equal to 1 over the initial concentration, right? And so this time, you do actually have to keep track of that negative sign here. We should actually have a positive sign for that slope. If it's negative, then it means that the rate constant is negative, and that won't physically make any sense. And so if we plot it this way, meaning we have specific concentration values, and instead of just plotting the concentration at time t, we plot 1 over that value versus the time. If we get a straight line, that means that we have a second order reaction. So generally, if you're given a set of data, and I believe one of the homework problems you are, right, you're given 2 columns of data. I think it's the concentration versus time, and it says what order reaction is this? Well, how do you know if you're just given the concentration versus time? Basically, you just plot it 3 different ways, and whichever one gives you a line tells you the order of that reaction. And so kind of a sequential, stepwise way you approach that is you collect the concentration versus time. Assuming first order, plot the natural log of A versus time. If it's linear graph is obtained, then it's first order. If no linear graph, then plot 1 over A versus time. And then what if that's not linear, then what are you going to plot? Zeroth order, right? So I'm going to add a step here. If no linear graph, plot A versus time. And then 7, if linear, then it's 0th order. All right, so for each one, you plot the data in a specific way. Natural log, 1 over A for A versus time. And whichever one gives you a line tells you the order of the reaction. So this is not the type of question that you would get on an exam without actually being given the plot. I'm not going to ask you guys to plot something, spend all that time going through that. Doing that manually with a calculator would be very tedious. But in lab, you'll be able to do that, and you can actually do this for in Excel relatively quickly, right? So in Excel, or if you want to use any other programming language, you're more than welcome to. You just plot you have your concentration data. You leave that data the same. That'll be your test for 0th order. Make a function for the next column as 1 over the value in the first column. Copy that down. That gives you the second order plot, and then you can do natural log of the very first column for the third column, and that gives you the second order plot. All right, so if you were given a series of data like what you have on your problem set, and that's what it's asking you to do, you're given the concentration value versus time, and you're going to determine if it's first or second order. For this question, it could also be 0th order, which means that you're going to plot these values two different ways, right? So this is just the concentration. You also have the ln of the concentration, and then 1 over the concentration of these values. And so I know I keep reinforcing this just because I think it's a foreign concept, but all you're doing for your y values here is you're just taking this value and you're saying natural log of that value gives me this value. Natural log of this value gives me the second time point. Then you do that for all of these, and then you just plot this column versus that column. And that gives you the manipulation of the data, right? Ultimately it's as simple as just plugging this into a calculator and getting a new y value. Then you do the exact same thing for 1 over this value, gives you the first time point, 1 over that value gives you the second time point, and so on and so forth, and you go all the way down. And so then you just plug that into, if you have a graphing calculator, you can do it in a graphing calculator. So this one right here would be ln 0.0100. This is ln 0.0087. This is 1 over 0.0100. This is 1 over, sorry, I know it's really messy, 0.0887. Right, and then you just continue that all the way down for each of these columns. And when you do that, you'll just see whichever plot is going to be linear, right? So here, for this specific reaction, you plot natural log versus time. Does it look like it's a linear plot here? Right, each of the data points are the black dots here, right? So that's just taking times 0, whatever the constant ln of that concentration value. This is the second time point, the natural log of that concentration gives me that value right there. And you see it doesn't match the line very well. There's still a curve to it. So this means that it is not first order. So this would not be a first order reaction. Why? Because these data points don't fit a line well. I mean, what do we mean don't fit a line well? Does anyone know any way you could quantitatively determine how well a fit is to a line? Has anyone taken a statistics course maybe? Or is anyone familiar with using Excel or Google Sheets? I don't expect you guys to just
Is
fit.
that what the R?
The R squared value, right? So you can plot an R squared value, right? And an R squared value is in between 0 and 1. 1 where 1 is linear and 0 is far from linear. And you guys will do this in the next lab, right? So this means that you have, if the R squared value for your plot is equal to 1, that means you have a perfectly linear plot. If it's less than 1, and then let's say usually below 0.9 or 0.95, then you say, okay, that's not a very good fit for that line. And it's R because what the software is actually calculating are what are called, residuals. When you try and fit it to the line, what are the leftover discrepancies between where the line is and where the data points are? So that's how we would know, okay, this is not a good fit. You can just look at this by eye and say, nope, that's not first order. If you had to do it quantitatively for a lab or something, then you would plot the R, or look at the R squared value and see how well of a fit it is. Chances are in our lab, you might mess up on the experiment a bit and your R squared values aren't really going to be good for any of them. Hopefully not, but that could be the case. So here we plot 1 over the concentration versus time. Does that look like it has a good fit? This looks like it does have a good fit, so then we would say this is what kind of reaction, or what order reaction? This is a second order reaction. And then the R squared value would be around 1 for this plot. And then once you have okay, this is a line, you can print the equation for the line. And why would you need the equation for the line here? Yep, because this gives us the value of K, and then this also gives us the initial concentration value for our data as well, right? So this is our value for K, and this is our 1 over the initial concentration, and we actually have nitrous oxide right there. That's our initial nitrous oxide concentration. That's like 0.01 is what the initial concentration will be. All right, so that's why we would actually plot the data for the line. So on an exam, I'd either give you the plot, or if I didn't give you the plot, it would be more of a explain how you would determine from this data first, second, or 0th order reaction. You'd say, okay, well, I go through the steps of plotting it all these different ways. And then I would say, well, how would you get the rate constant in that? Well, I'd get the equation for the line and then use this relationship. All right, any questions on the plotting of all the different rate laws, half-lives, integrated rate laws? Okay, and so here, on the lecture notes is a compiled list of what the different plots will look like when it matches the order of that reaction. We have the units for our rate constant in each of these. I know the resolution is kind of low, my bad. The units for each of the rate constants based off the order of the reaction, what the experimental rate law, the form of that is, the expression for the half-life, and then also a plot of what it looks like. All right, so order of the reaction is equal to what for the experimental rate law? How did you solve for the order of the reaction in the lab? Or what were you solving for? The exponent, right? So the order of the reaction is related to the exponent in the experimental rate law. Why is it called the experimental rate law? Because you can only get this by doing experiments, right? You can't tell this from the chemical reaction beforehand. You have to do an experiment to actually get that, get the dependence of the rate of the reaction on the concentration. So this was the exponent, was the order. This was determined experimentally. And that gives us a relationship between what two things? The experimental rate law?
The concentration
Mm-hmm.
and is it the rate of the reaction?
The rate of the reaction, right? So it's uppercase K, not to be confused with lowercase k, which is our rate constant, our proportionality constant, to make sure the units work out. It gives us a relationship between the rate of the reaction and the concentration of whatever the reactant is, right? The integrated rate laws, right, we derived those from the experimental rate laws, except those are different because they give us a relationship between what two things? Concentration and time. And we can use that data and plot it specific ways to then get the order of the reaction. And then we can also define the half-life based off of the integrated rate laws, right? So this half-life comes from the integrated rate law. From integrated rate law. And then there was one equation that we don't have up here, which had to do with the relationship between the temperature and the rate of the reaction. And what equation was that related those two things? The Arrhenius equation, right? So Arrhenius gives us a relationship between lowercase t and the temperature, lowercase t versus temperature, and that was K is equal to A e to the minus EA over RT. And so this encompasses pretty much everything that we've talked about up until this point. And this is the majority of kinetics, right? So kinetics is a study of how concentration changes with time. Because it's not built off of first principles and stuff, this is used to describe a lot of other things besides just chemistry, right? We can use kinetics to talk about population dynamics in biology, talk about non-equilibrium systems in physics and all these other things, right? Okay. So after this, maybe in the lab section today, we'll go over some of the extra questions here. The rest of the lecture slides here, at a certain point it starts going into the Arrhenius equation, but we did that, we covered that whole lecture in lab, so those notes will be posted with this as well. We did that before I think last Tuesday is when we talked about that. Okay, is there anything, you guys have any questions, burning questions about integrated rate laws, concentration?
For the Arrhenius equation, it's little k versus t.
Yep. Yeah, this is big K. And the reason I said the rate of the reaction, how it changes with time, is because based off of all these experimental rate laws, if little k changes with temperature, with temperature, then the rate of the reaction is changing with temperature. So because these two are directly proportional to each other, that means that the rate of the reaction also depends, right? So mathematically what I'm saying is that uppercase K can be equal to AE minus EA over RT times the concentration squared, for example, where that's the rate of the reaction. All I did is I just plugged in this into that expression right there. But really the temperature dependence shows up in how the rate constant depends on temperature. It's just how the rate constant depends on temperature is the same as how the rate of the reaction depends on temperature. And I know I'm saying rate constant, rate of reaction, a lot really close to each other, so I know that can be a little overwhelming. But we need to make sure that we're clear about which one we're talking to, or talking about. Or talking to if you're studying late at night. You'll start talking to the equations too. All right. Any other questions about these? Okay, so that'll be it for the part two